So our story begins in April of last year when our friends here at the Event Horizon Telescope collaboration released the very first image of a real black hole in the sky, namely the supermassive one in the center of M87. And this is the image that was released. And as you can see, there's a dark patch in the middle. That's where the black hole is, and it's surrounded by a ring of light with an asymmetric brightness profile. Now, of course, this is the very first image, and it's a little bit blurry. It's going to get better over time. And we think that eventually, once we are better able to resolve the image, it will look something like this, which is a GR-MHD simulated image of what we think the black hole at the center of M87 looks like. And what's striking about this is that the ring of light turns out to actually be a pencil-thin ring of light. And this is not a fine-tuned image that was cherry-picked to look like this. This is actually quite generic, and many GR-MHD simulated images display the same feature, a very thin ring of light, which has now been dubbed the photon ring. And in fact, if you look very closely, you'll see that within this band, which has a size of order m, the Schwarzschild radius, there's an even thinner and brighter ring. And we think that as you go to higher and higher resolution, the structure will be repeated over and over again, and then we'll see brighter and brighter and thinner rings on top of the first one that we can see here. So this raises a number of questions. What is this photon ring? What is its origin, and why is it consistent across all these images? How can we better experimentally resolve it and get an image that looks like the one I just showed you? And what can we learn from this experiment? So I'm going to give the punchline to the talk. It turns out that this photon ring is a universal, that is to say matter-independent, effect of general relativity. So it's insensitive to the astrophysical details of the source of emission around the black hole, and that's why it's present across all images. And this ring actually has a subring structure. It's composed of many subrings, and the structure is entirely governed by three critical parameters, gamma, delta, and tau, which have been computed recently. And this photon ring and its universal substructure are present in the image, such as we'll see, such as the one that I just showed you, as I'll show you in a bit. But the Event Horizon Telescope measures in Fourier space. And so the substructure is actually also present there. And the subrings produce strong and universal signatures on very long interferometric baselines. And those, we hope, will be detected by a future extension of the Event Horizon Telescope to space. And this is interesting because the signatures offer the possibility of very precise measurements of black hole mass and spin, as well as tests of general relativity in the strong field regime using only a sparse interferometric array.
Just a question, you mentioned three parameters, but they are actually just mass and spin. So fundamentally, you can reduce the three into two.
It's extremely over-constrained. These are, in fact, functions around the ring.
Mm-hmm.
So you're fitting three functions to two parameters. That's why we think this is very good.
And the ring, the light from the ring is lensed emission from the disk in other parts. So
I will explain exactly.
So would you have this independence of I guess initial conditions not really being sensitive to what type of disk you have or how, I mean, thick.
So whatever the source is, that gives you the first image,
mm-hmm.
which is the background. But then this ring feature is just the same emission lensed over and over again. So
mm-hmm.
once you know what the source is, that tells you the background image. But then this photon ring structure is just a self-similar repeated set of images of that same main emission. This will become clearer, hopefully, in a couple of slides. OK, so most of this story appeared in this paper that was released on the archive last summer. And I want to point out that it's a marriage of theory and experiment. This is a product of the Black Hole Initiative and a testament to the power of interdisciplinary work. And this paper brought together string theorists, numerical relativists, observers, instrumentalists, even a philosopher. And I think it's an example of what we can achieve when we all get together and study black holes from different perspectives. The paper will appear in Science Advances in a couple of months. And in the meantime, I've also written a couple of follow-up papers with Sam Grella, in which we describe some more fine features of this photon ring and its structure. OK, so the first thing I want to explain is what happens in the geometry of the Kerr black hole. So it is possible to have light rays that actually orbit a fixed radius, a fixed Bohr-Lindquist radius around the black hole, which is perhaps surprising. And Leo Stein has a website. If you go to his personal homepage, there's a 3D applet that lets you animate these geodesics, and I encourage you to play with them. It's very fun. And what you find is that it's possible within a certain region, which we've called the photon shell, it is possible to have light rays that in principle orbit indefinitely. Now, to be clear, it's not the case that every light ray here goes around. Of course, there are some that escape. But the point is that at any radius, it is possible to tune the parameters of a light ray. You can tune it to have critical parameters in just such a way that it will stay on an orbit of fixed radius. These are unstable orbits. But they describe this kind of 3D pattern. And as you can see here, as they go around, they sweep out some polar angle. And depending on the radius that you're at, you can go higher or lower. And we're going to define an orbit to be the motion of such a critical light ray as it goes from one turning point down to the other and then back. So that's one orbit. And so just going from the top to the bottom, that's a half orbit. And so two of the critical parameters are very easy to describe. You can ask, how long does it take for a light ray to complete half an orbit? So from the time it starts here to the time that it gets there. So that's called tau. And it varies with the radius. And then the other one, delta, is asking how much azimuthal angle phi is swept in this process. So as you can see, these guys go around. How much does it go around in phi per half orbit? So those are the two parameters, delta and tau. And then the third one has to do with the orbital instability of these bound orbits. So as I told you, if you start off here and you tune your parameters just right to be critical, the light ray that you shoot up will stay on a circle of fixed radius. But now suppose that you move it a little bit to the side. Now it's not perfectly tuned anymore. It's not critical, it's near critical. And because these are unstable orbits, it's going to escape. And in fact, you can use the geodesic deviation equation to find that the rate at which the radius will grow is actually, it's an exponential growth. And the rate is controlled by an exponent, so the Lyapunov exponent, which we've called gamma. And it tells you roughly the rate of exponential growth per half orbit in the deviation from the bound orbit.
A photon cannot be defined better than a wavelength.
Yes.
So there is a minimum leakage that
Yes.
is unavoidable just due to the spread of the wave function of the photon.
That's true.
And so it doesn't affect your ability to see the rings.
It is possible to, okay, so for the purpose of black hole images, the characteristic wavelength of a photon is very, very, very small.
Only 10 minus 12.
Yeah, but compared to the,
10 minus 12 of the horizon.
yeah, so compared to the mass of the black hole, yeah, so this is
10 to the minus 12, that's what I'm saying. The wavelength,
yes,
centimeter wavelength, is 10 minus 12 of the Schwarzschild radius of Sagittarius star.
correct.
Okay.
So yeah, there are,
So 10 to the 12 in the exponent is not a huge number. I mean, it will be 12 e-folds.
that's a lot.
12 e-folds? 12 dynamical times is not a long time. It's 12 hours, whatever. Within 12 hours, you lose every photon. If it's exponential on the dynamical time, I don't know what gamma is, but whatever.
Okay, so I'm not sure how to answer this precisely, but at least for n up to 6, which is what I'm going to care about, I think we're okay. It's an interesting question. What happens? There's a way to describe it also in terms of wave mechanics, which we've been trying to understand. And these parameters also enter in that description, but it's vastly more complicated. So because we're going to use the geometric optics approximation here, which should be fine because the wavelength of the photons is very small compared to the characteristic size of the black hole. And so corrections are suppressed by that ratio, which is
10 minus 12.
tiny. Okay, so yeah, this will not last forever, but it will last for hopefully a long enough time. Okay, so that's gamma. And now I'm going to shift gears and describe what are the implications for images of a black hole. So when we set up an image screen, okay, there are many ways to do this, but a convenient choice is to pick coordinates such that the origin is the line of sight to the black hole, and the vertical axis is the spin axis of the black hole projected onto your image screen. And then what happens is that if you shoot a light ray back, if you aim a light ray exactly at the black hole, naturally it goes in, crosses the event horizon, and is trapped. Now, if you aim a light ray slightly away from the black hole, it's still going to get sucked in because the gravity of the black hole will pull it in, and it will still get captured. On the other hand, if you aim a light ray very far away from the black hole, then you might get some deflection, but it'll escape to infinity. And so there's a region of capture and the region of escape, and those two are delineated by a boundary or separatrix, which we call the critical curve. And what happens there is that light rays that are aimed exactly on this critical curve get trapped by the black hole and orbit indefinitely in the photon shell. It's the boundary between capture and escape. And something that's very interesting about this is that depending on where you aim around this ring, around this curve, the light ray gets trapped at a different radius. So if I aim here or here, my light ray will eventually be trapped at a smaller or larger radius. So increasing radius goes this way. This is a funny feature of black hole lensing. It's really the bending of space-time brought to life on your screen, because usually you're used to thinking that if you look around a star, you're seeing around the star in its geometry, but here you look around the image, but actually in the geometry you're varying the radius, which is very bizarre. And so as I said, a critical light ray is one that's aimed exactly in this curve and is captured by the photon shell, where it'll in principle orbit the black hole forever, unstably. And there's a funny feature here that every point on this curve is really a whole sphere in the geometry, which is suggestive perhaps of holography, and I have some speculation about this if you want to ask me after the talk. But for the purpose of astrophysics, what we're interested in are the near critical light rays. So those are those that are aimed very close to this curve, and in principle can execute multiple orbits before they eventually either get captured if they're inside the curve, or eventually escape if they're outside the curve. So how many times do they orbit? Well, it turns out you can do a calculation, and you find that as you move in the perpendicular direction d from this critical curve, you find that the number of orbits performed diverges logarithmically with a coefficient that's controlled by the orbital instability gamma, the Lyapunov exponent. So what I've done on this slide is I've taken an image of a black hole, and this axis is literally this axis, and this axis is literally this axis. And I'm asking the question, if I shoot a light ray back and maximally extend it either to the horizon or to infinity, how many orbits around the black hole does it perform? The solid curve is the exact result, and the dotted line is this logarithmic approximation here, which, as you can see, is excellent. And if you invert this relation, it tells you that if you want to aim a light ray in such a way that it executes an additional orbit, half orbit, so you want n to increase by 1, you have to aim a distance that's exponentially closer to the critical curve. Okay?
What are the units on the x-axis?
So these are units of m. Good question, I should have said this. So if there were no bending by gravity, if we're in flat space, and the event horizon, say we have an extremal black hole with radius m, then it would be the circle here. But of course, because there's bending of space-time, in fact, any light ray aimed in here gets to cross the event horizon. Okay, but the point is, as you aim the light ray closer, there's a logarithmic divergence. And the one thing I want you to note for now, because I'll refer to it later, is that you can see that when you're within m of this critical curve, already it's enough to describe an additional half turn. So this is important, and I'll refer back to this again. But for now, what I want to say is that if you try to compute, using GRMHD and radiative transfer, a simulated image of ME7, what you're supposed to do is that you shoot a light ray back, and whenever it crosses matter, you load photons onto the light ray according to radiative transfer. But roughly, what that means is that if you have a light ray that completes n turns through the shell, it's going to pick up roughly n times more photons than a light ray that just crosses once. And so roughly, the intensity that you collect along the ray, and therefore how bright the corresponding pixel is, should scale like n. And so for optically thin matter distributions, this implies this logarithmic divergence in n implies a mild logarithmic divergence in the observed ring intensity near the critical curve. And the photon ring that we saw on the first GRMHD simulated image is the bump in the photon intensity, which contains this logarithmic divergence that arises due to the existence of these near critical orbits. Now, of course, there are many effects that cut this off. Avi pointed out, leakage and wave mechanics. There are also propagation effects. So there's also a finite optical depth. But nonetheless, the striking feature remains visually prominent in many of the ray-traced images of GRMHD simulations. And in fact, if you take a state-of-the-art numerical simulation that George Wong prepared for our paper, if you take this image and you consider, say, a horizontal and a vertical cut, it doesn't really matter. You get these blue and red profiles of the intensity. And if we zoom in on them, then what we see is that effectively there's a background image, that's the n equals 0 direct emission that's coming from the source. And then on top of that, there's the same image from light rays that go around an extra half orbit that's squeezed in on top. And we see this repeating pattern happen again, at least up to n equals 3. I think they went up to n equals 6 in the best simulations. And this does take into account propagation effects that we can handle analytically. So this is something that survives at least once you put those features in.
So just a question. So when we see the image, are we probing the horizon at all, or just the photon ring? We never get closer than the photon ring to the black hole when we look at the image.
So the light rays that you aim in here,
Yeah.
if you follow them all
They
the way
follow.
back, they cross on
So
the
we
black
never
hole.
see, so we are not probing really the horizon, we're just probing a few times the horizon.
So maybe what you're asking, one question you could ask is, these photons that we see in here, where were they loaded onto the light ray? Probably not that close to the horizon, because the redshift effects as well too.
So this doesn't prove the existence of a horizon, this image.
Well, there's a dark patch in the middle. So I think what I'm saying is a little orthogonal to that, but of course, and I think you can argue from this image, dark patch, black hole. And also, the fact that there's this ring structure, okay, we didn't resolve it to such a high resolution, but this ring structure arises because of these bound orbits.
Sure, but you
And
can have
black
them
holes-
around a neutron star also. In principle, you can have a neutron star with a photon ring around it.
Avi, we can't prove anything.
No, with LIGO you are getting close to the horizon.
But you still can't prove it's a
Actually, I'm not sure about that, because I think that the photon star is bigger than its Schwarzschild radius, and the photon shell is close to the Schwarzschild radius. So it could be that for a neutron star, if it's not spinning, then the only radius at which orbits can be bound is 3m. So I suspect, I'm not sure off the cuff, but I suspect that for a neutron star, its radius is bigger than 3 times its mass. And so I think there are no actual orbiting orbits for a star. So you wouldn't get a photon ring. Hope I'm right about this.
Somebody in the room must know how big radius is in terms of.
Is it bigger than 3m? Probably, right?
Well, we have neutron stars of 2 solar masses, and we know that the radius is 12 kilometers or less. So 2 solar masses has a Schwarzschild radius of, has m equals 3 kilometers. So 4m is roughly, 3 to 4m is the neutron stars we know about. 3 to 4m are the smallest.
Okay, so they would
The
include.
radius is 12
kilometers. Yeah, for all of them, independent of mass. That's what people
But-
find.
So it's
No, but if the
two-
radius is 3 to 4m,
M
then
is 1.5 kilometers.
Right. No, 2 solar masses.
Oh,
So
2
it's-
solar
So it's 3
masses.
kilometers.
It's too big.
So it's 4m.
so it doesn't have a photon shell. It's inside the star.
But
So
that's-
you're not going to get.
But that's for a nuclear equation of state, though. You could, if you want to go to theory land, you could cook up some crazy equation of state, and you could give an event horizon. I'm sorry, some sort of object which had radius of just outside the Schwarzschild radius.
Yeah, I think the odds are stacked against this. Probably, I'd be surprised if you could cook out the scenario in which you get a neutron star to have a photon ring. But if you could do it, that would be a cool proof of concept. Okay, so let me say a few words about this. Now, the photons, which comprise these successive subrings at a given angle r, so here we're just showing horizontal and vertical cuts, but at any angle that you look around the ring, you get this wedding cake structure, and the photons which comprise successive subrings will traverse essentially the same orbits and therefore encounter the same matter distribution around the black hole. So what that means is that apart from source variations on the timescale of an orbit, we think that the nth and n plus 1th subring should differ only because they correspond to windows that are exponentially narrow. And so that leads us to write these approximate relations. The height, the intensity loaded on through each pass should be the same. So that's saying that the height of these layers is roughly the same. That's this equation. But because they're exponentially squeezed by this factor of e to the minus gamma, this demagnification factor, the total amount of flux that you get should be suppressed by e to the minus gamma as you go from one subring to the next. Okay, now these formulas are matter-independent predictions for the photon ring substructure, which only involve GR. And of course, these predictions hold only for large enough n. Mathematically, it's a 1 over n expansion. And it's small n, so n equals 0, 1, 2. There are non-universal matter-dependent effects. But it seems like already n equals 2 is in this universal regime from the simulations. OK. So I just want to quickly point out that this explains the two most prominent features that are visible across GRMHD simulated images of M87. So the first feature is that we have direct emission, the n equals 0 background, which is superposed with a bright pencil-thin ring. And its width, as I said earlier, you can see that if you're within m of the critical curve, it's already enough to complete an extra half orbit and therefore hit the matter, the emission region a second time. So that predicts the width, which should be of order m. I should have said the diameter here is about 10 m, and so this width is of order m. So we can qualitatively match that. And the n equals 1 subring, which is the thicker band, should carry about e to the minus gamma, which is roughly 10% of the total flux in the image, and that is indeed the case in GRMHD simulated images. So this logarithmic approximation is enough to get the mean features.
I mean, is it always the case that the background is, I mean, there's a lot less flux density in the background than the ring? Can you reduce the density contrast? Can you think of a scenario where you'd have, almost equal flux per unit area in the n equals 0 region as you do in the n equals 1, etc.?
Well, the flux is much smaller here because the n equals 1 is much smaller. The intensity is the brightness of the pixel, and yes, the intensity here is the intensity at a pixel here is half of the intensity of a pixel here, because here you just have twice.
But do you think you can reduce this density contrast?
Yeah, so two things. One, this doesn't look, the difference looks big on this image, but that's just kind of an illusion. The difference is not as big, first of all. And second, most GRMHD simulated images that the EHT produce look roughly like this, and I think there are external constraints like jet power and how much emission you get in the X-ray, which prefer such model. But yeah, I think in principle you could make the background brighter. That's a question for...
Is this time average?
This is a time average.
Right, so that's also changing this contrast, right? If you look at a snapshot, you would have much...
There will be
denser.
flares, that's right, that's right. Okay. And the second feature is the brightness asymmetry around the ring. And obviously that's due to relativistic beaming. So there's a redshift effect. The spin on the image is pointing here, and so the matter that's on the lower side is coming at you, whereas the matter on the upper side is moving away from you. But I want to point out that there's a second effect, which is that as you look around the ring, you're seeing different radii in the geometry. So the lower part is also the closest region to the horizon, whereas the upper part is the region farthest away. And astronomers prefer models with power law fall-offs, so the inner region of emission is always hotter. And so that actually contributes to the asymmetry. OK, so what I've told you so far is that general relativity predicts that embedded with the image of a black hole lies a thin photon ring, and it's composed of a sequence of self-similar subrings. And each subring is a lensed image of the main emission, which is indexed by the number n of photon half-orbits executed around the black hole. And in the last few months, we've really developed a complete analytic theory of this problem. And so to quickly show you how it works, let's consider a simple example where we're looking exactly from the axis at an equatorial disk. And let's consider a single point source. It turns out that a single point source will produce a sequence of images, which arise from light rays that go around more and more times. And the sequence is completely characterized by gamma, delta, tau, which control the demagnification, rotation, and time delay of successive images, respectively. So in particular, if you get an image at a distance dn from the critical curve, which is here in black, at some angle phi n around it, and at some time Tn, then the next image from a light ray that executes an additional orbit will be time delayed by delta, which makes sense because it arose from a ray that did an extra half turn and swept an extra angle. Sorry, it rotates by delta and it's time delayed by tau, which is what the light ray does in the geometry. And it's exponentially demagnified by e to the minus gamma. So if you saw from the nth image this color wheel, then the next image that you would see from an additional lensing effect would look like this. So depending on the spin of the black hole, you'll have a bigger or smaller demagnification. If the black hole is Schwarzschild, then you get a rotation of exactly pi. So the color wheel rotates exactly half a turn. As you increase the spin, it can go up to 3/4 of a turn. But the time delay is roughly constant. It's always about 16 m, which for M87 is about 6 days. So if you were to look at movies of black holes of the black hole in M87, you might search for autocorrelations in the photon ring on the order of 6 days.
Sorry, what is meant by spin being 100% or 50%?
A over m.
Oh,
Sorry. Yeah.
So in other words, looking for echoes.
Light echoes. Yeah. So the characteristic time scale of light echoes in the photon ring is about 6 days for M87 or 16 m in general. And so that applies for the light rays that are bent a lot, but it's interesting that even the direct image, basically, if it's emitted from radius rs, then the radius on your image is described by this linear relationship, which is just adding 1. So it's actually surprisingly simple. That's a feature of the Bohr-Lindquist coordinates, but it means that for both the direct and highly bent geodesics, you can basically do the ray tracing by hand. It's very simple. Okay, so now I want to talk a little bit about EHT measurements. But I want you to keep in mind this fact, the direct emission, the n equals 0 light, depends on the nature of the source, and that's astrophysics, and it's not universal. But once you know that background, then the photon ring structure, which is the n equals 1 and greater subrings, will consist of just exponentially demagnified images of that main emission. So whatever n equals 0 is, that I can't tell you. But once you know n equals 0, the repeated pattern on top of that is just a reflection of general relativity. It's universal. And I think that answers your question, right?
But I guess I was also concerned with what n equals 0 actually is, because
yeah, so that's astrophysics. But given the astrophysical background, the pattern of repeated images, that's GR. That's all I can tell you.
Yeah, so I just hope that they're sampling well enough with enough plausible, physically motivated initial conditions that you're not just choosing a really biased or prejudiced set of initial conditions that are just going to give you results that are fairly universal. I mean, there could be emission processes that are more characteristic of outflows. Some of them are more characteristic
so again,
of inflows.
Whatever that does, it'll change the background emission. But the ring structure, that's always going to be there as long as you have GR in the Kerr geometry. Okay, so I don't have time to explain interferometry, but I just want to get to the final plot, and so I need to say a few words. We're after the image, so the intensity is a function of location on the screen. But what the event horizon measures is its Fourier transform. And so for the purpose of this discussion, all you need to know is that if you have a delta function ring in your image, so this is your intensity profile, then the visibility, which is what the EHT samples, will be a Bessel function J0. And if you go to large baselines, so you take the legs of your interferometer and you separate them, so large separation between the legs, long baseline is large U. You can Taylor expand this in 1 over U. And at large U, you find that the signal decays like an inverse power law, 1 over root U. And it rings with a frequency which is set by the diameter of the ring. So what that looks like is that you get this ringing pattern, and the size of a hop is the diameter of the shadow, or this critical curve, which, by the way, if you can measure to high accuracy by sampling many hops, would help you determine the spin of the black hole and its mass to high accuracy. But the thing I want to point out here is that, of course, these rings are not delta function thin rings. And so when you get to baselines, so the x-axis here, this is a log-log plot, and this is baseline. Once you get to very long baselines, say of order 1 over the width of the ring, then you start to notice that it's actually not a delta function. And so once you resolve it, you have some exponential fall off. But once that happens, wait a second, there's a second subring, which is exponentially narrower. So that one will look like a delta function for an exponentially longer baseline until you get to 1 over the width of that subring, at which point it gets resolved, exponentially dies off. But if you have many, many subrings, you get this cascading pattern where every time you get to 1 over the width of a subring, it dies off, but then the next one takes over, and the envelope of this cascade is 1 over u to the 3/2, so it should survive for a very long time. And the ratio of these step sizes is the ratio of the widths of each successive subring, so that's e to the gamma, the demagnification factor. So you can measure the diameter of the shadow from the hops, and you can measure the demagnification factor from the ratio of the step size.
By the way, this is identical to what you get in baryonic acoustic oscillations in cosmology, because there you have a sound horizon, which is a ring, and you take the Fourier transform of that, although you do it in 3 dimensions, but you get these rings, exactly the same.
Yeah,
it's really nice.
One of the fun things about this is learning how Fourier transforms into 2D work. There's a lot of beautiful structure. And the takeaway here is that the baseline is the distance between the legs of the interferometer measured in units of the observation wavelength. So to go to longer baselines, you can do 2 things. You can increase the observation frequency, or you can increase the distance between the observer legs, which is what we're doing, the interferometer legs. And so you can see that depending on what frequency you observe at and what the distance between your detectors is, you might be able to get different subrings resolved. And this is where the EHT in 2017 was. But if you were able to go to a terahertz and put a telescope on the moon, you'd be able to see the n=2 subring. And if you go to the Lagrange points between the Earth and the Sun, L2, you might be able to see also the n=3. And just like we tested the prediction for the intensity profile from the numerical simulation in image space, we also looked at it in Fourier space. So for that same time average GR image desimulated image that I was showing you before, the same horizontal vertical cut, you can now go to Fourier space and look at the visibility amplitudes as a function of baseline length. This is for a snapshot, and you can see that in the snapshot it's a little messier, but once you time average, it becomes very clean. So low baselines, you get all the details of the astrophysics, the disk, and the jet. But once you get to long enough baselines, you start to resolve the n=1 photon ring, and you enter the photon ring GR-dominated regime. This is astrophysics, and then everything else is GR. And you can see n=0, n=1, n=2. And of course, we need to go to higher resolution and have more sophisticated simulations to really understand how this works, but it looks very promising. Okay, so to conclude, the takeaway is, on the theory side, there's a photon shell, which is a region of space-time that's spanned by bound photon orbits. And there are these critical exponents gamma, which determine the exponential rate of deviation of the nearly bound orbits. The photon ring is the image in the observer sky of the photon shell and its nearby geodesics. It consists of this self-similar sequence of subrings, which are labeled by half-orbit number n. And each subring is an image of the entire photon shell emission, which is demagnified by e to the minus gamma. The Lyapunov exponents are measurable fundamental quantities that flow only from GR and encode spin. And the bright ring in the image of ME7 is the first such ring. And on the experimental side, there's a separation between the astrophysics and GR-dominated regime as you go from short to long baselines. And I think there's an exciting prospect for space-based interferometry and a future extension of EHT to space, which might allow us to see, with a single baseline, possibly resolve the n=1, 2, and maybe even 3 subrings. Thank you.
Questions for Alex? Ali.
You could be more ambitious than that because you're limiting yourself to millimeter wavelength. But if you were to work in the infrared, that's a factor of 1,000 shorter wavelength. So with a baseline that is 1,000 times shorter, you could achieve the same resolution. But so you might go to more than n=2. That's what I'm saying. In principle, of course, it's much more challenging in the infrared.
Well, you run into optical depth effects, of course. I mean, if you're that close to the black hole.
No, not in the, well, it depends what infrared wavelength, but in principle you can see through the dust if you go to.
But it turns out maybe lower frequencies might need a ticket, because then if you go up to higher Z, then you naturally are looking at higher frequencies that as they left the black hole. So you can get around that optical depth effect at even lower frequencies.
Mm-hmm.
There's another competing effect, though, which is the higher you go in frequency, the more optically thin the emission region
Right.
is. And so if you go to lower frequencies, you'll start to worry about absorption effects.
I was talking about higher frequency.
Yeah,
Yeah,
exactly.
yeah, yeah.
So then that helps you. That's
Yeah,
right.
but
That
we
helps
can't
you.
do VLBI yet with IR, which is
Yeah.
Well,
Yeah.
you can do it on tens of meters right now.
tens of meters. Well, the VLTI,
Yeah,
like
exactly.
gravity.
But people are talking about 100 meters. They're doing experiments.
What about in space? Is it hard to do in space?
Well,
Different
it's-
wavelengths
it-
in space?
It's just hard to maintain coherence at that frequency. You know, so you need to be able to do the interferometry, and the difficulty is that it's hard to make heterodyne receivers at those high frequencies. I mean, you can get around it at some point. I mean, if you do real-time interferometry.
Yeah, I don't know what the best way to measure it, but I really hope it happens.
Well, you have AHT. By the way, it should not. The name should be changed. It's the Photon Ring telescope, rather than Event Horizon telescope.
It doesn't have the same charm. I'm sorry.
I heard somebody say the PRI, the Photon Ring Imager. No, okay, I see. All right, let's stick to Event Horizon telescope.
I bet the Lyapunov exponent device.
Zero funding.
Further questions for Alex? All right, let's thank him again.
Before the introduction, I wanted to mention we have a visitor, a long-term visitor for 3 weeks. Anna Aegis is here, and she's in the back over there. Whoever would like to interact, she works on cosmology and philosophy. Well, she used to a long time ago.
10 years ago.
10 years ago. But you still have it in your DNA.
Well, that
academic
has a lot
thing.
of things in the DNA, right?
Okay, our second speaker is Lydia Bieri. She's a professor of math from University of Michigan, and she'll be speaking to us about gravitational memory.
Well, thank you very much, and thank the host again for inviting me. It's always a pleasure to come back here and interact with everybody. So I'm gonna talk, I'm a mathematician by training, but I hope to speak to everybody in this room. So I'm gonna explain more about spacetimes and mathematical structures of spacetimes and impacts that we find in gravitational waves and the memory effect. So we'll see. So first of all, I will focus mostly on asymptotically flat spacetimes. So when we want to understand gravitational objects like a galaxy, black holes, etc., we think of them, well, as an initial value problem in GR for the Einstein equations. So we look at the snapshot in time. I'll actually take a picture at some point, try to convert that into mathematical language, and I try to see for an open set of data what kind of spacetimes can I create and what are the null asymptotics looking like. So I will talk a little bit about that, and especially I'm going to concentrate on some new results, look a little bit into some deeper structures and what could be seen probably in gravitational waves, and especially memory effect, or how would that affect this. So of course GR is governed by the Einstein equations, and on the left-hand side, of course, we have curvature. On the right-hand side, you plug in any kind of matter or energy fields that you like, and you have to, of course, always add the fields on the right-hand side. If you have, for instance, electromagnetic fields, you look at the system of equations. We call it the Einstein maximum equations, for instance. So, well, and maybe just a little bit philosophically, from the mathematical point of view, it's always interesting to have, let's say, one specific solution of the Einstein equations, but you can only get so much out of it. So if you want to really understand the dynamics, etc., of the Einstein equations, you look at some initial data set. Maybe draw a picture over here. So I have, maybe at some time, t = 0. I take this picture, but then I'm interested in kind of all kinds of data, not just one special solution, but data that is asymptotically flat. Some stuff is happening locally, and then my space-time or the initial data decays towards flat Minkowski space at infinity. So we look at large classes of space-time. So an open set of initial data, and then we want to solve the Einstein equations and see what happens in the future. what happens in the future, and then of course, for instance, when gravitational waves are sent out, so they travel for a long time, so we take an idealization, say time goes to infinity, and that's where we do the observations up here. So that's where we see gravitational waves. What we do is really, so what happens here is we look backwards in time along null hypersurfaces. So I will call these light cones, but these are actually interesting null hypersurfaces with a lot of geometric structure.
So what sort of norm or measure would you use to assess flatness? And do you care about the rate at which something becomes asymptotically
I will
flat?
tell that in a few slides. I mean, that's exactly the point, because there is all kinds of different data. I mean, maybe people have worked with the residual Klein spacetimes, or stuff that is more general than that. I will make that precise in formulas in a few minutes. Okay, so then from the gravitational radiation point of view, and also for memory, so we are interested in what kind of data gives you what kind of classes. So you have an open set of classes of spacetimes, and then we want to study what's happening here, and things are really interesting sometimes locally, but then certain things survive at null infinity, and certain things can be said, written, or read off of the gravitational waves. Okay, so most often, maybe for most of the talk, I'll just concentrate on the Einstein vacuum equations. If you put the right-hand side equal to 0, then you have only the Einstein vacuum equations. And again, they are really, I mean, there's a lot of beautiful structure in there. I mean, a result a few years ago, for instance, of Chrysodoulou showed if you have focusing of gravitational waves, energy in gravitational waves, you can form a trapped surface and eventually a black hole. So these are just purely gravitational results, for instance. So for what I'm going to present, I will use a time function t and an optical function, so what I call null hypersurfaces Cu. So you can think of these as light cones, gravitational waves, light is traveling along those, and I will, so this is an interesting structure, so I foliate my space-time with an optical function U, that solves an iconal equation in the space-time, and I have my time function t. And interesting enough, sometimes when, let's say, the whole problem, hyperbolic PDEs are too hard to solve, you restrict yourself locally on this sphere. Basically, it's topologically a sphere when you have a time space-like hypersurface intersected with a null cone. So then you have this two-sphere, and you can actually mathematically solve certain problems. Are much simpler there. They reduce to some elliptic equations, and then you can go along again the null hypersurfaces or the space-like hypersurface and recover the full hyperbolic problem in here. So this is just technically, maybe I write something like that down here. So for the geometry or the setting I'm looking at, so maybe I have here a null cone going out, HT. So then this is my intersection. You can think of it as a sphere of these. And I will introduce the frame, and L and L bar are null vector fields. So if I look into the outgoing null direction, that will be my frame E4 equals L. And the ingoing vector field is called E3. So this will be important when I decompose the curvature and other objects. And then E1 and 2 are just an orthonormal frame on this field. It's just a technical thing. Now again, when things happen, let's say this is the sphere, you can think also when interesting things happen somewhere locally, then again, gravitational waves are sent out, they travel along these null hypersurfaces. And the geometric objects that will actually dominate what's going on are the shears. So I can write down the shear with respect to the outgoing and with respect to the incoming cone. And if you think the chi bar, basically if I take the absolute value squared, you can think of this as the News function. So in the physics terms. So this type of shears will come up when I want to understand gravitational memory later. Again, so this is probably I said, but maybe one thing, and I will give you now a few spacetimes or initial data types with different fall-off. So, and Chrysodoulou-Kleinemann type spacetime, so they had this breakthrough result in the 90s where they showed that Minkowski space is stable. You would say, well, you have initial data which is small enough in certain weighted Sobolev norms, and then you have a global solution of the Einstein equations which do not form black holes or anything, which are globally actually geodesically complete. Now, their data, their proof relies on some smallness assumption. However, what they also achieve is a really good structure that goes out to null infinity, so the structure along the null cones. And these structures along the null cones actually are independent of the smallness. Now, Kerr stability is another thing that has not yet been proven, probably very close to that. But let's say if we have the point of view right now, well, these black holes with angular momentum exist. So, and well, yes, they exist once we have, let's say that once we accept that they exist, you can say the null directions, the geometry of these null directions are independent of the smallness, so we can use some of this data that was used, for instance, by Christodoulou-Kleinemann under a smallness assumption for large stuff. So what we do on the null hypersurfaces is independent from small data. You can plug in large data. So that's the motivation also. So we want to understand how these spacetimes look like, how the structures are, whereas locally a lot of stuff is completely different. But the null structures are independent from the smallness. And so we can use these also to large data. So let me maybe just put that. This is the Christodoulou-Kleinemann result. I'll give you a formula in a moment. But this is really that you perturb Minkowski space, you plug in something which is asymptotically flat, and you get this global result. And many people have worked on generalizations for those, but before I go there, let me now give you the data. So this is the type of initial data that Christodoulou and Kleinemann use, and interesting for us in terms of what's going on now, also with radiation for plugging large data, is a type of fall-off. So M here is just the mass, the ADM mass. So you have a 2m/r term basically in there, and then some decay of the tail of the metric, like r to the minus 3/2, for instance. And when you look at this type of data, so a lot of things come out nicely. You have one type, you can read off a lot for gravitational waves, etc. that I will tell you in a moment. So from here you can ask, well, what if you don't have this symmetry basically here? What if you generalize more? What could there be? I mean, this 1/r term is really what you believe from astrophysics. This is the stuff that exists out in nature, but what if you have other kind of weird things? How far can you go? So in my thesis, that's a while ago, a few years ago, I generalized that result to the actually borderline case in terms of stability. So again, that's a small data assumption in the beginning, but on the other hand, we can relax it and plug in large data and still rely on the null asymptotic geometric picture that we get. So between this, and this, there's a lot of interesting questions you can ask, weird terms that can show up, and the question is what kind of things will actually have an impact in gravitational waves and memory, and what other things will not, or what can we learn about all that? Yeah.
So you're not demanding that the mass is finite?
No.
Allowing infinite mass?
No. So that's an interesting question, because the mass itself, neither in Christodoulou-Kleinemann nor in that paper, does not play a role, but it comes out as a consequence of the proof that the mass is not big. I mean, in the stability proof itself, you know. So the mass itself there's no assumption on the mass from the beginning. The way we have to control the curvature and the space-time geometric objects is by using the Bell-Robinson tensor. So that's our energy tensor. This has to be controlled. And what comes out in the Christodoulou-Kleinemann case, as well as in my extension, is way here.
Sorry,
is
I'm not understanding. I mean, it looks like the Christodoulou-Kleinemann are assuming the mass is n.
Mm-hmm.
But if it goes like 1/√r, the mass wouldn't be defined, right?
It is actually defined. This goes back to a result by Robert Bartnick. So he showed that for this type of fall-off data, and even actually a little bit less regularity, he has O2 here, two derivatives. He shows that the mass, as well as the linear ADM linear momentum, the ADM definition, are well defined. I do not have angular momentum here. It is not defined. I mean, it's not defined. It's too rough, the data. But there's no assumption that the mass is small. There's an assumption that this Bell-Robinson tensor has to be small enough. Okay. So, and again, maybe here's the mathematical definition of null infinity. So that's where we are sitting and looking backwards in space-time, and we look at gravitational waves. And, well, I added the black hole definition because I think it's a neat kind of geometric definition of the black hole here. So for null infinity, again, interesting for us is that what happens, what do we understand from looking at this dynamics of these space-times? We want to know how things survive. And what I'm going to do, I want to say a few words about gravitational radiation generally, but then I go deeper into the details of these different space-times. So for the Christodoulou-Kleinemann type, just for the moment, maybe you can just stay with alpha bar. Alpha bar is the leading order curvature term that goes like 1/r. Tau minus, you can think of this as u, the optical function which is foliating my space-time into these null hypersurfaces. And so the leading order curvature part is just this alpha bar that goes like 1 over r. So in that case, so the alpha bar is the 1 over r in the Christodoulou-Kleinema setting curvature term. And well, all these have, of course, interesting behavior, etc. And so when I look now at the data that I actually looked at, so I get, if you look at the Christodoulou-Kleinema result, you get all kind of, peeling up to here and then it fails. That's another interesting thing. Penrose suggested that there's peeling, that the next order curvature terms, if you add more decay in the data, that you get an r to the minus 4, r to the minus 5. And then Christodoulou showed that actually no, you pick up a log term for beta, you get an r to the minus 4 log r for physical situations. But so anyway. And so with the very slow decay that I had, I get a 1 over r decay also for the leading order term, and of course less in u. And then the other things are just not, I didn't ask for a lot of decay, so then you can only get as much out as you ask for. So there's some stuff here. And now, interesting questions are, you asked one, is ADM mass defined? Yes, it is defined. And even Bondi mass comes out finite. And if you look at that, it's not clear, because when these things actually don't have limits, it's, for instance, the rho, that part of the curvature comes into the mass aspect function and then into the Bondi mass. But still, certain things cancel out, and I can say that in a moment. So between these kind of spacetimes here, in the type, if you have a lot of, maybe here, if you have a lot of enough decay, then things are nice enough and well defined, and you can in a straightforward manner work with them. And in this borderline case that I just showed you, that's for the stability proof. If you relax this r to the minus 1/2, you don't get things explode, so you don't get the stability anymore. So within these classes of spacetimes, from this borderline case to the hard more decay, there's a lot of stuff that happens in between. You have polyhomogeneous terms, you have all kind of logarithmic terms, etc., that can show up. So for what classes of spacetimes, what can occur, what are actually the solutions of the Einstein equations, and how would they affect gravitational wave and memory? So of course, when we look at gravitational wave sources, like two black holes colliding, so they send out the waves here, and at the same time they are following their curve. For the memory effect, so maybe another picture, I think the memory effect of gravitational waves is then a permanent displacement of the test masses. If this is like in LIGO, the test masses, so when the wave train comes through, they move, and what GR predicts is that there will be a permanent displacement of these test masses with respect to each other. So the space-time before and after the wave have passed is different. So you can think of it, if you subtract all the stuff around you, from going from one Minkowski space into another Minkowski space. So this was first in a linearized version written down by Silnovich and Polnareff in the 70s, by Christodoulou in the fully nonlinear case on the beginning of the 90s. And interesting enough, there's been a lot of work now, and also in other fields recently, and with Andy and a lot of people, there's a lot of people working on memory analogs in other fields, etc. I don't have enough time to go into that, and the point of my talk is now to talk about space-time structures, so I will not go and discuss more about this. But what turned out, that these are actually two types of memory effects, which are so Garfinkel and I showed that the two memories that I just showed you, this in the linear setting and the nonlinear setting, are actually not due to the linear nonlinear case, but these are two different effects, which do the same thing. So the ordinary memory is sourced by one curvature component. So if you contract, let's say, your curvature, Riemannian curvature into the 3 bar direction. So this is what I basically call rho, is a constant in front, doesn't matter. So this comes into this is the limit of this rho is p at null infinity. So this thing has a limit at null infinity, and so you can think of it as the electric part of the Weil curvature. And the null memory, which is what Christodoulou computed, is really, if you look at, if you don't have that, if you just look at the Einstein vacuum equation, so it's the News tensor, that square that you integrate over all of null infinity. And then with several collaborations, we showed that also the stress energy of other fields will contribute to this memory effect and make the effect bigger, actually. All right, so these are two different effects. And now the question is, in all these kind of different space-times, we can think of what happens really to the ordinary and to the null effect. So first,
for weak gravitational waves, do these two effects come in the same order in 1 over r, or different orders?
so if you look at that, so it's the same order in the end. It's the same order. I have some formulas in a moment. Okay, so let me first maybe address the parity of gravitational waves. So for a while, people thought there was magnetic parity of the gravitational memory effect, but actually we can show that there's only, so that the memory for gravitational waves is actually only of electric parity. So let us look at that maybe from this point of view. So this I said already, so just to remind you of the setup I'm using. So we can, for the wild curvature of our Einstein vacuum space-time, I can decompose it into electric and magnetic part. It's an analogy to electromagnetism. So we have the electric part of the wild, the magnetic part of the wild curvature, and then I can write basically the geodesic equation measuring the separation of test particles, so the acceleration basically, down as an equation where the acceleration on the left-hand side is governed by the electric part of the wild curvature. So that's the Jacobi equation. Well, that's a simple equation, and so let me first focus on what's going on here. And so for the electric and magnetic parts, so I can think of maybe also some more pictures here. Here again, I'm somewhere on this sphere. So n is here a normal to this intersection of a cone with the space-like hypersurface. N is just the outward normal that lies completely in the space-like hypersurface. Well, I look at some special components. So the NN component, so if I contract towards the NN component of the electric part is what I call rho. The HNN component, that's the magnetic part, is sigma. So maybe just to say the electric part, that's rho, and then the magnetic part, that's sigma here. Okay. And the equations I wrote down here is over some really simple relations that survive at null infinity. Here, beta bar is, well, the r to the minus 2 component of the curvature that shows up, which is related to the shear, which gives us the News function. And then the two shears are the shear and the leading order curvature component at null infinity. These are the limits of those are related through that. And here the two shears are also related to each other. So this will play a role in. Now, let us look at the Bianchi equations. And so in my notation, alpha bar again is the leading order curvature component. Beta bar is the second, the r to the minus order curvature component. 3 is the ingoing null direction. 4 is the outgoing null direction. So this is just part of the Bianchi equations. And I can see, well, lower order terms are neglected for the moment. So if I just look at these two Bianchi equations, I take a derivative into the ingoing null direction, then I see that, first of all, this is an interesting equation. This I will use to compute the memory now, both the null and the ordinary memory. And after that, I will discuss what kind of space-times have what implications in these equations. So when I look at that, so if I take the Christodoulou-Kahneman spacetimes for a moment, I mean, even in my ones, so for this equation, so that is of order r to the minus 3, even in the most general setting. So this is fine, but in the setting that this most, let's see, really the slowly falling off space-times have not enough decay here to put this on the left-hand side. So there is some issue that there's only an r to the minus 5½ decay that we have to deal with. So what we can do is I manipulate this a little bit, just geometric equation. So I see, well, I can write it this way, the right-hand side, and say, well, I have now a derivative of this object, the two shears, the chi-hat bar, and I have this thing, the trace chi goes like 1 over r chi-hat bar squared, that's the News. And what I can do is I can take this on the left-hand side for the moment, and then of course what I have here is of order r to the minus 3. So what I would like to achieve is I want to have something which has a limit at null infinity. So this actually, if I multiply with r to the 3, so actually has a limit at null infinity, and this is the limiting equation. So I have the curvature component here, the divergence of that, and the News tensor, and then I just give the left-hand side some name for the moment. So even in this very slowly decaying space-times, I can do something here. So let's go on and say, well, if we integrate now, I'm at null infinity, so u is my function that, I mean, goes to minus and plus infinity. It's kind of a it's my function living, it's a retarded time function at null infinity. So what happens now if I take limits of that, this is the curvature component that also comes into the mass aspect function. That's the curvature component which has limits at positive when u goes to plus and minus infinity, so it's non-zero limits. Then, well, I get this equation for the beta term, and then I get that one, which is, I mean, the News tensor, right? And now if I look at this, so if I plug this all into the equation from before, I get this nice equation where now for the memory effect, so this thing here, this is the object I want to understand. So basically, the easy thing to say is that the delta x, the permanent displacement that we will see, that's not a Laplacian, just a delta x, is some constant times this sigma stuff over there, sigma minus minus sigma plus. Don't worry about that, there's some constant in before, but basically the delta x is governed by this shear asymptotic expression. And now these are equations on the sphere at null infinity, so I can solve them completely. And this is the null memory, the contribution from the null memory effect. And this is the ordinary memory. So that's the ordinary memory effect. That's a part of the electric Weil tensor, or the 3-4-3-4 part. So let's look at that for the moment. So in all the space-times that decay like 1 over r, basically, this is all well-defined and finite. If you go and relax now to the very general case that I presented before, then I can show this is still finite and well-defined, and it's just a borderline case, this null memory. These two things don't have a limit at null infinity, respectively diverge. Let me say a little bit more about that. Maybe I have to jump. I'll go back to the previous slide in a moment, but let me jump here for the moment. So this kind of space-time, so K is second fundamental form, so like, yeah. So for instance, if I have the chi-hat is the shear where basically that makes up the News tensor. So this is always something like r to the minus 1 and some decay in u. Let me just call it minus x, depending on what kind of space-time you live in. So if you have, let's say, K is a more general, it's a second fundamental form, but actually chi-hat is kind of included in there. So let's just put it like that. So if you have like in the crystallo-Kleiner space-time that this r goes like, this is an overall decay, r to the minus 5/2 would mean that the chi-hat is r to the minus 1, u to the minus 3/2. So this means just a general decay in the initial data slice. So then this means for space-times of this type where the k, the second fundamental form, is of r to the minus 2 and just a little bit, a little epsilon. This is all fine. You can actually, the ordinary memory is still finite. And then if you have this situation where you don't have enough decay for this thing has not a limit. I still have a limit for the chi-hat bar, but then the sigma, the other shear, does not have a limit at null infinity. So what happens here is then that we can show we still have a finite null memory, but the ordinary memory actually diverges like a square root of r or u. And then what cannot occur, so you cannot have this situation. So if you have just a bare exact r to the minus 2, that will give you a logarithmically divergent ordinary memory. That cannot happen. So we have shown if you plug that in this kind of data, so there's some issue, it does not solve the Einstein equations. Moreover, if you have just a single term like that, you can always transform it away. So this ordinary memory will either diverge fast, I mean with, for instance, square root of u, or it will be finite. So going back maybe to the electric and magnetic question, there's still the question, can there be a magnetic parity, etc., of the waves? So let's look at that. That's now an equation on such a sphere. Theta is just the torsion of these cones. Mu bar is the mass aspect function. Rho is the, again, electric part of the curvature. Sigma is the magnetic part of the curvature and the shears. Now, if I look at that system and I look at it at null infinity, the interesting part, why do we have actually limits for rho? And could there be also a limit for sigma at null infinity? So that would mean we have a magnetic part of the wave as well. So here what we can show is, well, if you look at the data for all these spacetimes, let's look at the spacetimes, not the general ones, but that go like 1 over r epsilon. So then we can show this always has a limit, but this sigma actually decays in U. So it will never contribute anything to the memory effect there. So that's the problem. So we study this kind of equation on a sphere at infinity, and then we take the limits and we show that, so for all this type of space-times, I can show you that in a formula, this sigma, this magnetic part of the curvature actually decays in U. I think I have it somewhere, sorry. Okay, so the way to show that is basically you look at these classes of space-times, and even if you take the very slow fall off, where this, let's say, the curvature does not really, the rho and sigma do not have a limit at null infinity, so then you can show the null limits for these do not exist, but you can show from these equations that I just showed you that the mean value of this sigma, of the magnetic part, still exists, so that actually has a value and it decays in U. So even for the space-times that do not produce limits for these curvature components at null infinity, you show that the mean value actually decays in U. So that's so much for the parity. So there's no magnetic parity for this memory. However, there was an interesting example brought up by Bob Wald and his student Gautam. So they looked at some stress energy of some dust shell, etc. So they are not able to write down equations for that, but it's something, just a philosophical Gedanken experiment to write down something that would actually give you a magnetic part for ordinary memory. So null memory is always electric, there's no magnetic part showing up, you can exclude that by computation. But then for the magnetic part, everything we have seen or known in astrophysics so far will have only electric parity, but this example is really interesting because it creates a magnetic memory also, but we don't know the equations for these things. Maybe in the last 2 minutes or so, I'll say a little bit more about different structures. So between this very general setting of data, there's a lot going on. There's a lot of logarithmic terms, for instance, etc., appearing at different orders. And something we have been able to show last year is, so you do not get a logarithmically divergent ordinary memory. So null memory is always finite, but the divergence is faster, so like square root, for instance, in the limiting case. And for solutions that we know that decay like any astrophysical object, I think we have seen it's only electric. So that's just maybe a little remark. Even in these very general classes of space-times, even though the mu component does not have a limit, we still get a Bondi mass which is finite. And that's due to the fact that certain things cancel out. So the Bondi mass itself is well defined, is finite. And this is the null memory energy formula, so this is just borderline. If you relax now the data, but just an epsilon, this will not be finite anymore. Anyway, so something just the most recent things we have been studying. So we said, well, let's see, there's a lot of classes of space-times, or let's say initial data, and we can produce solutions that are interesting. And when you go and look at lower order effects now, not just the higher order, but also lower order effects, would we see those things? So we have looked at the classes of space-times to see, well, if I don't impose any condition, for instance, what kind of solutions do we get, what kind of structures do we get? And then we found, well, it depends also that we found a lot of, let's say, logarithmic terms at different orders, etc., that might play an interesting role when one looks at angular momentum also. So things show up at lower order. And so recently I've seen that, well, if you impose, let's say, the no incoming radiation condition at past null infinity, so then certain classes of space-times that, let's say, or initial data that would not solve the Einstein equations without any conditions suddenly solve the Einstein equations. So you kind of get, by imposing at null, minus null infinity, some no incoming radiation condition, you kind of erase in the initial hypersurface certain terms that, well, make it possible for you to have, you can solve the Einstein equations, and you get, so these equations pick up, for instance, some logarithmic terms that are not at past null infinity, but they are there at plus null infinity. So we have, I'm not going to show you the formulas for those, but just basically some stuff you can plug in some log terms at different orders, or also other terms, etc. And it's interesting that when you go to past null infinity and you impose this condition, then there's a much larger classes of spacetimes that actually can be that solve the Einstein equations. And interesting enough, so we have all kind of structures that probably, if you don't depose anything, you look at the most general cases, so it looks pretty straightforward from minus to plus infinity. But if you impose these conditions, for instance, you can see, oh wow, there's stuff going on, so your equations pick up certain terms, like log terms in the evolution to future null infinity. I'm not showing the formulas for that, but I would say that's interesting. I would like to motivate, people who are interested to look at deeper structures in these space-times. So if you go to lower order, not only maybe of one solution, but lower order of classes of space-times and see how these things interact. And probably, I don't know, maybe in the future these things will also maybe show up and be able, gravitational wave and wave memory in some ways, so you need more precision for that. But I think there's a lot of interesting structures when we dig deeper, but yeah, okay, I would like to motivate this kind of discussion. Thank you.
Questions for Lydia?
I have a basic question.
Yeah.
When you showed the Jacobi equation, there was only the electric part on the right-hand side.
Mm-hmm.
So doesn't that tell you already? I think I've missed something. Doesn't that tell you already there's
No,
only
if you go back so to this thing here, so for the memory effect, right? So if you look at the memory effect.
Yeah, so the test masses only deviate by
Mm-hmm.
a part that earlier you had the Jacobi equation.
Yeah, so maybe I have to go somewhere else. The Jacobi equation is for the gravitational.
Yeah, this one. 50.
Right, exactly. But now let me take you to the other set of the two equations I had. This one. So let's take this to null infinity. That's again. This is an equation on the sphere, and if I take the limits at null infinity, theta is the torsion. And now I can do the same. I can also get the memory formula out of these, right? I can get the memory formula out of this by manipulating this term. And then that will be the ordinary, so the limits of these will give me the ordinary memory. This mu bar is going to be Bondi mass, so basically I can translate this into the energy radiated away with the News tensor. And this theta is actually going to so this is going to translate into the sigma, my little formula, the delta x is the sigma over there. So yes, but the sigma, this shear, actually there's a curl equation also. So it could be that, generally it could be that from here to this, so this theta contributes to the sigma, if this, it could be a contribution from that equation.
I see.
So that's why.
Thank you.
Further questions?
Yeah, I've got an observer kind of question. So if you wanted to observe this, how big is this shift and in what circumstances?
Right. So the field strength that, LIGO has been observing is 10 to the minus 21, so to the lambda over lambda, right? So this would be at the order 10 to the minus 22. And there has been, but the big question is here really for ground-based detectors, there's a lot of noise. This is a low frequency event, so from epsilon to maybe 10 hertz, something like that. Mm-hmm. And so this is where all the noise is, so it's very challenging actually to get rid of the noise there.
So the signal is millihertz, but this effect is in the 10 hertz or something?
Well, between, I call it epsilon, and maybe 10, it depends. So.
There was a paper trying to ask whether a lot of LIGO events can be together stacked.
Yes.
Yeah,
I just wanted to mention that exactly. So because I've talked to these people. So Yuri Levin, there's 5 of them, I think. There have been 2 papers in the LIGO collaboration saying, well, you could stack these events, the black hole mergers, and hopefully with more events, then the probability gets higher to see something.
So maybe it will be detected. Maybe.
Yeah.
They say.
Is it different with LISA? Because, how does this scale with?
Should be much better.
Yeah. LISA has a very high signal to noise.
So,
yeah, maybe.
But not in that frequency.
But we have to wait a decade. We're young enough.
I know. You're young enough, Bob.
Okay, no further questions, then let's actually
Yeah, sure.
Yeah.
So before you take off, we should chat soon. What are we going to chat about? Well, I've got a 3 o'clock, but let's not let
Okay,
too
this week,
long
it
go
will be
by.
5 minutes. I know, I'll find you.
Thanks. Thanks for listening, thanks for talking.
Well, thank you.
Great.
So what's space-time which decay like root of r, like 1 over root of r? How should I, as a physicist, how should I think about them? Like,
That's a good
is
question.
There, is there some
No.
example or?
No, astrophysically, the example only 1 over r. So this
Yeah.
is all I have so far. But you can think of this in a way. Oh, okay, I don't know. Question is, could it be that, I mean, maybe some weird object or at some point where certain things maybe still have a long range, etc. Maybe something like that can exist somewhere in a very deep way. But what actually mathematically the question was really how far can you go? So what is the borderline case? Because at some point you cannot do that anymore. Physically, I think it's interesting also for different reasons between that very boundary case and the things that we have.
You mean r to the minus
r to
half?
minus 1/2.
Yeah.
That's the boundary case. Okay. So between that and let's say crystal plasma and another space-time like 1 over r, there's a lot of stuff in between.
Right, but even as a physicist, even r to the minus 2/3 doesn't make sense to me already.
Yeah, I know.
It seems like infinite math.
But I mean, some physicists,
maybe it's a different
some
way of going to
physicists
knowledge.
claim the following thing,
Okay.
and this is something they actually disprove. So this was from physics papers, not us. So r to the minus 1 log r.
Mm-hmm. That we do find sometimes in physical examples.
So I think so. There's 2 things. If you have something like that, so there was actually some papers claiming that ordinary matter because of that decays or not decays that diverges like logarithmical. But we showed that this is not the case. And
These are the
moreover-
IR divergences that Andy and friends were also.
No, that's different.
That's different. Okay.
That's something else. But if it's so for me, astrophysically, what we know is 1 over r decay in general. But I mean, I would like to see maybe in some sense, right? If you look at the question is also if you are really could it be that there's something which is maybe not gravitationally that strong, like everything like 1 over r, that could have some tail effect, etc. Somehow. So that's maybe the most physical. Mathematically, it was just to see how far can we go. Physically, for me, there's 2 interesting things. Maybe there's stuff out there, I don't know, that for some reason could have a tail which is very slowly decaying, that could still affect things in one way or another. But also between, not r to the minus 3/2, but just between this square root 1 over r, square root of r and stuff more like this log r things.
Yeah.
So is there anything that could have that behavior? And looking at these things, so we show yes, there are certain type of solutions that exist, but then again, if you zoom in more with the log type, only some of them actually solve the equations.
You said something about that somehow you can get rid of these logs by coordinate transformations. Or something
Yeah,
like
that's
that.
the funny thing. So this
Okay.
whole business of that. So if you have, let's say, a metric, or let's say, in the initial metric.
That does resonate like with things that I've encountered.
Yeah, something for r to the minus, let's say, if you just take r to the minus 1 for now, let's just take that. And if you compute all your curvature components, etc., then at some point you will end up with a curvature component, let me just call it a curvature component that looks like you have a decay of, let's say, r to the minus 3, and then what I call optical function is the retarded time, u to the minus 1. And then you have to integrate that component over u, so you get basically a log u divergence, right? And we showed this is not, so there are 2 things. If you have just one linear vector like that, first of all, if you don't impose any extra conditions, it's not a solution of the answer equations, because, I mean, some Bianchi equations are not fulfilled. If you impose no incoming radiation, you can actually remedy that, but this you can always transform away. So if you have just one term like that, and this logarithmic divergence, so you can always do a coordinate transformation to get rid of that one.
I see.
But now you can ask other things. You can say, well, I can have maybe a cascade of infinitely many, like, I can actually put that stuff in by hand, and maybe instead of having that, maybe put in some log u terms in here. That would give me maybe log u to the n, stuff like that, and then it would even have more weird things. And then what we found if you put stuff like this is, you can transform away, but if you put stuff like this, or some stuff like r minus 1 log r even by hand in there, so if you, or not r, but let's say, you have then u, the log terms show up in u, not in r, let's say. You still have, this is still physical, but then you plug in your log terms in u, for instance, right? Stuff like that. If you have finitely many,